Hello, everyone. Thank you for your patience, and welcome to this meetup with Elasticsearch. We are going to have a section about hybrid search and then some QA. And this is a meetup organized by Barcelona UG and hosted by Adaptive and with the collaboration of Apiumhub. And before we start, I have to ask you a question. Could you raise your hand if this is your first time coming to a Barcelona UG meetup? Okay, we have more than one. I need to do this presentation. Sorry for the other ones that has come before. So who we are? We are a bunch of enthusiasts and people from very different disciplines that are related to the Java world, but not only. And we are a legal association that is based here in Barcelona since 2012, so we have now 11 years. And we are 2,200 members already. What do? We meet usually twice a month to discuss about technologies and solutions and ideas, and anything that will help grow the developer community in Barcelona. Yes, we work with Java, but not only. We also discuss DevOps and cloud computing, agility, anything that you have in mind about software development, we are interested. So if you want to follow us, we have several QR links here. In Twitter, we normally post pictures and links about the events we are going to have in the future. And in YouTube, we record some sessions like this one today, and we upload it so you can watch it afterwards. And also, we have recordings from our previous conference editions. We also post on LinkedIn. We have a meetup if you want to keep posted about future events. There is a Flickr page that we don't use anymore, so I need to remove this. Well, some past events we have had this year and the year before. As you can see, we have touched many topics from AWS, Apache Camel, Hazelcast, Neo4j, Docker, Quarkus, Kafka, OpenTelemetry. We should put Elastic here as well, because there have been 2 meetups already. But yes, in the center we have Java, but this is not only our topic of interest. And we would like to thank Adaptive today for hosting this meetup. I don't know, Natalia, do you want to say something?
Yeah, sure.
Okay.
Thank you. And the micro, I think, right? Please.
Ah.
So, let's see. Yeah, it's working now. Is it working for me as well? Okay, that's great. Okay, so thanks everyone for coming in today. It's like the first event we hold since the pandemic hit, so it's pretty exciting to see new faces. And I haven't practiced since then, so bear with me while I'm doing the presentation. So yeah, before I say a few sentences or lines about Adaptive, just a little housekeeping detail. You all have a card that has been given to you downstairs. If you're planning to leave the event before we all finish, please come to talk. I mean, no, it's fine. You can let me know, but you have to drop the card downstairs in the slot. I think that you've been told by the woman downstairs. But if you're planning to go outside for a smoke or anything like that, come and talk to us, because you're not going to be able to come back in. So we'll give you another card, and then you can bring it back. That one, yeah. So you can talk to Angel. So yeah, just a few lines about Adaptive. We were also founded in 2012 in London with 4 friends who were working together. We're also really passionate about tech, and they just wanted to build the kind of company they wanted to work for. What this means is that they were looking to have a place with interesting and challenging projects, a great culture and environment, a place where they could share knowledge and basically collaborate and grow together. Since then, we've gone from 4 people in 10 years to be around 300 employees now, and globally, and we're in 4 different locations: London, Barcelona, Montreal, and New York. No. We can say that, but we're going to be disclosing more info soon. And yeah, although we have a hybrid working policy at the moment, we're still keeping the offices for this. Although I know that some of you are looking for fully remote work. And yeah, we also recently, but last year, we acquired RealLogic. Not sure if you've heard of Aaron, but if I could keep talking about different things, but if you want to have some information, you can scan our Linktree code, and you'll have all our social media links to the reactive trader, etc., etc. But I know you haven't come to listen to me, so I'm gonna let Mabi introduce them. Do you need just this?
Okay, professional. Okay. Hi everyone, thanks for coming. We're here on behalf of Apiumhub. Apiumhub is a software development hub based here in Barcelona. We specialize in software architecture, back-end development, front-end, and also mobile as well. As Anu said, we're going to be recording the sessions in case you're interested in rewatching them later. We'll be posting them on our YouTube channel. Thanks.
Okay, one last thing. So if you are interested in working with us, if you have any idea for a talk, a workshop, a coding dojo, maybe an open panel, anything that's on your mind about software development and Java, talk to us. We can make it possible. We can discuss how to do it. So we are open. We have this email, and we also have a Slack channel, so you can keep in touch. And without further ado, I present you Philipp. One last thing. If you registered for our meetup and paid €2, you can talk to me if you want them back. Normally we bring a paper that you signed and you confirm that you attended, but I forgot it. So you just please tell me I attended, I paid the €2, I want them back. We will make the arrangement. And yes, now I present you Philipp.
I have my own.
You have your own.
I think. I hope. Let me see. I'll move slightly over so I'm less in the picture. Thank you. But no. How did that work again? This one. Perfect. Okay, everybody can see the screen. I guess we're good. Hi, I'm Philipp. I work for Elastic. I've been working for Elastic for a long time. I realize I think I've been with the company for more than 7 years at this point. And a lot of things have changed. So when I joined Elastic back in 2016, it was mostly about search. And then we started with logs, and then we went full observability and security. And I don't want to say that this talk is bringing us back to the roots of the company, but search is kind of like the hot new thing again because of things happening. And that's mostly around vector and hybrid search. And I want to show you a bit like what is hot around search and what we can generally do there. So I'll take a very quick look at classic or traditional search, what we have been doing for decades. And I think the theory for that comes out of the, 70s or something like that. And then we'll get to the newer machine learning based vector search and hybrid search models. And since no talk is complete nowadays without ChatGPT or OpenAI, we'll shortly touch on that, how that plays into search as well. So we'll try to cover all of this. If you have any questions at any point, just stop me and we'll try to figure out how to resolve that or redo the question or the answer that it makes more sense. Because it can be a confusing topic just because all of this machine learning stuff is currently at this phase where it's like both exciting and confusing. And there's a very rapid development, and things that used to be in a certain way 2 months ago are not longer relevant or the right way. So things are changing quite fast. So let's go into that. The tagline of Elasticsearch has been since 2010 when it started, been Elasticsearch, you know, for search. And that has always been the tagline, even though when we were focusing a lot on observability or security, search is still what powers all the other solutions. And how does that work? We have Apache Lucene as the library under the covers to do the actual search. And Elasticsearch is then doing the distribution, the query DSL, and makes sure that your data is where it is. But Lucene is actually doing the work there. And we are still contributing a lot to Lucene to bring it to the point where we need it, including vector search, which is also mostly implemented in Lucene, actually. So who remembers from Star Wars, from the very first movie, when he made that hand gesture, what was the phrase in Star Wars at this point? Yeah.
These are not the droids you're looking for.
Yes, and so I think the last time I was doing this talk was on May 4th, so it had to be Star Wars, but I liked it enough that I stuck to Star Wars as the example. So we'll keep Star Wars. How does full text search in the traditional sense work? I'm taking the sentence, these are not, with an emphasis, the droids you are looking for. And then to store that, first off, in search you would throw out the HTML because nobody's going to search for the emphasis tag. Then I use the standard tokenizer, which in not in Western languages, unlike Chinese, Japanese, etc., is relatively straightforward because it basically breaks up on white spaces and punctuation marks and removes them. And then what we do is we lowercase all of those tokens, because most people don't search for upper or lowercase, but just the lowercase form, so we lowercase it. We remove the so-called stop words, which are very common words that appear in almost every sentence. So they are very noisy, but you don't find something relevant. For example, the is a stop word, because it's very common. And then we do stemming with snowball stemmer, which is basically reducing the word down to the word root, or stem. So we don't care about plural or singular, or like look, looking, looks. We care about the concept of look, or the term. So that's what we want to reduce to. Who wants to guess what you get out of this? So when I use _analyze, I basically take this sentence, run it through that analysis chain, and then just get a few tokens out that would be stored for full text search. Who wants to guess what the remaining tokens here are? Yeah, so
Like that.
let's see, we can actually try this out. So I have, is this large enough for everybody to see? I'll make it slightly larger. I have 8.8, which hasn't been released yet, so I hope I don't run into any bugs, but this will come out pretty soon. I'm using 1 or 2 features from the upcoming release already. So this is the next minor release that we'll do, and I'll run my sentence through this pipeline, and let's see what we get out of here. So we get droid, you, look. Yeah, so it's, in this example, like there are a lot of stop words. In other phrases, we can try out another sentence just for the example. You won't lose that many tokens. What is interesting here is, so what Elasticsearch would be storing, I'm not actually storing anything, I'm just simulating here with the _analyze endpoint. So we would take droid, you, look, and we include the position. Why do we include the position in that?
Relevance?
And yeah, kind of. This is mostly for phrase search. If you, I mean, it's a weird phrase if you search for droid you, but if somebody searches for droid you would see that one is directly followed by the other. And by the way, how this is stored is the index structure is called an inverted index. So basically, we take all the tokens that we extract, we sort them alphabetically, and then we point back to the document where these tokens appear. And then if somebody searches for something, we'll run through the same analysis pipeline, and then the remaining tokens we just look up in that alphabetically sorted list. They will point back to the right documents, and these are then what we retrieve. And that is what makes search so fast. Unlike in a relational database, when you do a like search, it has to reanalyze every single string, and that's what makes it pretty slow. So here we do most of the work up front, and that's what makes search fast. So we store the position. We also store the start and end offset. Why are we doing that? For highlighting. So if you say, I want to highlight my search term, if you have a very long text, it doesn't need to reanalyze the text, but it can just say, you search for droid. I know that droid starts here and ends here, and then you can basically set the markers, and you don't need to reanalyze anything. This is alphanumeric. Anybody wants to guess what might be an alternative to alphanumeric? It could be a synonym. So you could say a droid is, I don't know, a robot. So if somebody searches for robot, they should also find droid. And then the type would be a synonym. And this is basically what we're storing. And then for search, we run through the same pipeline, and we retrieve the tokens that we find. This is kind of dumb or limited, but that also makes it very fast and scalable. And that was good enough for a long time. But as you can see, it's kind of very simplistic, because it's like you have just these tokens, and if you have, I don't know, if somebody searches for watch, for example, or search maybe, then it won't match unless you have defined a synonym, and that's a very tedious process. So you often don't find the relevant stuff, and it takes a lot of manual tuning to get this right. So that is where vector search and the machine learning models come into play, where this is a good starting point and it's fast, but it might not give you the full flexibility or the full feature set of what might be possible. Yeah, you've seen this. We haven't officially changed the tagline, and we'll keep evolving this a bit. But we do a lot of vector search nowadays. So let's dive into vector search and see what is vector search. So what you do in vector search is, the input is not necessarily just a document, a text document, but it could also be an image or an audio file. And then you basically extract a vector representation. I assume everybody still remembers vectors from school. When you were drawing in a 2 or 3 dimensional space, you were drawing something out, and then you had to redo it. So this is how we want to represent our documents. And we have probably more than 3 dimensions, but let's say we have 3 dimensions here in our example. And then the search query also gets transformed to a vector representation. And then you find or look for similar vectors, so vectors that are close to each other. And the idea is that these vectors that we generate represent whatever we have here as the input represents that. So it's not based on just a term, but it really represents the meaning of what we're trying to search. And it gives us options. For example, you could search for some audio file that sounds similar to another audio file. So if you have the right encoder or transformer to get some meaning out of that audio, you could find similar things or similar images. So this is not just for terms anymore, but this is really the similarity that we're trying to find through the representation of vectors. I hope that kind of makes sense. Let's look again at what a vector is, because I always found it hard to explain to others what a vector is. So this is not how this works. This is just trying to explain how vector representation could work. Bag of words is, let's say we have, these are not the droids you are looking for, and no, I am your father. Another good Star Wars quote. Do you want to guess what, if we use the previous approach, what no, I am your father, what you would have left? What, just for trying that out, I'll just copy this. No, I am your father, I think was the phrase. And here you get, I am your father. So this one doesn't have so many stop words. Yep, those are not stop words. Actually, the list of English stop words is very short. I think it's 33 words only. But this is language specific. So every language has a some linguists came up with the rules like this makes most sense for language X. I would need to check for Spanish how many stop words you have and what the rules are for stemming. But English is a pretty simple language, like the S for the plural or the third person singular and ing and those endings. So you just cut those off. So this is pretty simple. So this is what this would do. In my example, and this is totally made up, by the way, what I'm doing here is I basically take, I didn't remove stop words here. I just said these is the first term and then R is the second one. And R appears twice here because R. So this appears once, this appears twice, once, etc. So I basically count how many times does each token appear. And then I just take the same order that my terms appear from the first and the second document. And then I encode those as a vector. So these are my dimensions. These are not that. These are all my dimensions. And then I say like this has basically the vector has the distance or length of 1, this one 2, 1, etc. And this one, these are all 0, 1, only here it starts. These are the terms that are in there as well. But this is basically the representation of a vector for these sentences in a bag of words. The machine learning models are much more complicated and not bound to these terms because this is very expensive, and you can see it's very sparse because if you have like 10,000 terms, most sentences will only include a couple of those terms, and like most of those will be 0, and very few will only have a 1. So the machine learning models that we use nowadays are generally dense, so every vector has a value, and it might just not be an integer, but it could be any floating point value. But the idea is that you can represent a sentence in some form of vector. And bag of words is just the simplest example I could think of to try to explain how vectors can represent a sentence. It's not necessary that the vectors are really mapped out to the outside, but it's like the machine learning model will have like these dimensions of what means something. But just to give you a second example, this one has only 2 dimensions, this example, realistic and cartoon and mammal and bird. And then you see you have these various animals in various shapes. And here as the vectors, you can see where they are. And then let's assume you have something that is close to this vector here. You could see like how far or close the other ones are, and you could find the closest animal to the search term. So you would encode the search query as a vector as well, and then you would look for the closest vectors as the most relevant search hits. In reality, the machine learning models, they don't map to explicit or like it to terms, but they just have some kind of meaning encoded, and they will also have more dimensions, like 100 or 300 dimensions are pretty common to encode what some piece of information means. So what is a model of how to get to these vectors? There is Hugging Face, where Meta and many other big companies have uploaded their models of how to represent text or audio or images as these vectors. That's where you can get those vectors. And we have in Elastic, we have a Python library called eland that can import those models with the Python library is PyTorch. That's the logo for PyTorch. You can basically import a model from Hugging Face into the Elastic Stack, and then you have these as models available. And then when you store a document, Elastic or Elasticsearch actually can generate the vectors for a text for you. When you search, it can generate the vector for your search text and then find similar texts based on the vectors. How that might look like, here we take BERT Mini LM L6, which is one model that works for texts well. We import that into the Elastic Stack through eland, and then we have that available on the machine learning node in Elastic, and then we can encode the vectors out of a text. And there are a couple of libraries or ways or things that this can do. So for example, we can do named entity recognition. It can detect something is a person or a place or an origin or whatever, and then it can annotate that. That can be helpful just to find relevant things in a sentence. But it can also be used for other almost unexpected use cases. For example, a more security-related use case would be if you have PII data, the personally identifiable data, and you run that named entity recognition over your logs, and then you see that there is potentially some named entity in there that might be a person, for example, that you want to clean up before you store it in your logs. So these machine learning models can do a lot for full-text search, but you can also use them in other contexts. You can have this text embedding of encoding the text. You can have a classification of what type of text something is. Zero shot is if you don't need to train it yourself anymore, but this will just give it a best shot answer. Question and answer is you give it a question and then it formulates an answer out of the found documents, for example. So for example, you have a longer document and you say, give me an abbreviated answer for this question, and then question answer can extract a subset of a sentence or an answer for your question answering. How to or where to find models and how to use them. Hugging Face has a huge library. There is OpenAI's Clip is pretty good for images from what I've heard. You can also develop your own models if you have a data scientist in your team and label data, because that's normally the precondition. That might give you great results, but it requires way more effort. And I'll show you a bit like what we do around hybrid search and how you can kind of like get the best of the traditional search and the vector search in combination. So how do you search all of this? What you basically do is we store the model in a machine learning node, which we call then where we can do the inference. So basically, we have data that we want to store, and the data can either be text, then we throw it against that inference API, and it will get those embeddings out of my text, for example. If you have binary data, Elasticsearch is not very good with binary data. So there you would need to do that inference outside of the Elastic Stack, because we will not generate you a vector representation for binary data like an image or audio. In any case, once you have the vector representation, you can store it. Then when a user comes in with a query, you do the inference for the search, get the vectors as well. You do the k nearest neighbor search, where you find the closest vectors, and that is then what you return to your application. So this is kind of like the full life cycle of how to store your data to generate those vectors, and your query gets also vectorized, and then you search for similar vectors for the search results. That is what is falling out of these. Yeah, sure.
If I understand it correctly, in the end, it's like you are indexing the document, but just the vectors that you get from the model.
Yes.
When you index something, in reality, what you are doing is just indexing the result of passing the document through the model.
Yeah, so we store the original document normally because that's what you want to retrieve. But we store mostly also the vector because this is what you want to search on in vector search. Okay. Exactly. And that can look something like this. So either we store a document, this is like the classic approach. You see we have an ID, a product name, a description, a price, whatever. It's like all normal fields. Or you do that inference where you run it against the machine learning pipeline, and there you have a model, and that model then gives you the representation of, for example, one field where we say we want to have the description, our best-selling whatever, and that is represented by the description embedding, and that is like an array of floating point numbers. So this is this vector model. And then your query gets represented as something similar like that, and you find what is closest in vectors. And then how to search that. So vector search or KNN search was added in 8.0, so more than a year ago in Elasticsearch. In a very early versions, it had a dedicated endpoint which was _KNN_search. That has since then been replaced, and it's all rolled into the regular _search endpoint. What we're doing here is we're using a classic filter, so we are only filtering on things from the women's department and want 10 documents back. So this is a classic search, but then we don't do a match, for example, for a term, but we do the vector search. So here on the description of the embedding, we want to search for these, something that is similar to this vector. And then we get, just from this subset of the data, we find the similar vectors and get those documents back. Before 8.6, if I'm not mistaken, you had to infer that vector representation for the query in a separate step yourself manually. Since 8.6, I think, or 8.7, you don't have to provide the vectors, but you can just say, like, use this machine learning model, take this text, and within the query, generate the vector representation of this query, and then search that against what you have stored. So it's now only a single step to go from summer clothes, the text, to the vector representation and retrieving the document, so it's one single query anymore. It's just a bit easier to handle now. So how does all of that vector searching really work? How this is implemented under the hood is the thing that I can never pronounce correctly. It's hierarchical navigable small word, or HNSW. And how that kind of works, and this is like a rough representation. You have multiple layers, and this is like, these are all the vectors that you have, and you have layers that have less or fewer details. And you start at a random node in here, and you always try to get closer to the search match that you have. Because so these are these navigable small worlds. So these vectors are connected, some of those are connected, and this is how you get closer to those. So our starting point is this random node here, and we see that this node here is closer to our search vector, so we move to that one. Then we go to the next layer, which has more nodes already. We go to a node that is closer again to where we want to go. And then we go to another one with this one has all the layers. Green is kind of like where we want to be, and like the local optimal solution that we find in our vectors is this node here. This is the closest node that we have to the search term that we want to have. That is how this navigable small worlds work behind the scenes. It's all under the hood. You don't need to worry about it. I just try to explain like how this works, and it's not just magic that works somehow, but this is kind of like the model that is implemented under the hood. There is also, because brute forcing that has scales with in big O notation n, whereas these navigable small worlds have log n of all the documents. It depends on which subset of, if you have a filter of the documents you want to retrieve. So if you have a very small subset of the filter that we have shown before, you can just brute force it, and that will be faster. If you search the majority of your document in an index with the vector search, then this navigable worlds approach is faster, and that's how you will search them. So it has two different implementations to keep your queries fast. And how that works with these worlds is that you have this arbitrary starting node that was red in the previous example, and this is the query vector. This is what you're searching for, that, I don't know, cross. And then pink is nodes included by the filter, and gray is nodes excluded by the filter. And then you're traversing, and you're trying to get closer to that. And this is just trying to show you, if you have many things that are within the filter, you will do this small world navigating between the axes. And if you have few, you just do a brute force approach between the very few remaining ones to find the local optimum, to find the closest vector. So these are the implementation details. I don't want to get too hung up on the implementation details, just to show you how this works. One thing that's often coming up for discussion is like, how many dimensions should I have in my vectors? And the initial approach is often that people say like all of the dimensions, or as many as possible, because then I can express better what I'm trying to search. However, there is quite some cost to dimensions. So Lucene up until Elasticsearch 8.7 only supports 1024 dimensions. With 8.8, we will support 2000 dimensions. That does not mean you should use 2000 dimensions, because that still will need a lot of memory and also take longer to find. So your users will have to wait longer. So this is just what is generally possible. And I've had a couple of discussions on Twitter where people were like, but what if I want to use more? What if this is not enough? We might increase it later on. Most users that we know out there with larger document foundations, they will use like something like 300 dimensions or so at most, because otherwise it gets too expensive. Because to keep the search fast, you need to have almost all the vectors in memory, off heap, but still in memory. Otherwise, your search will be very slow, and you probably don't want to do that. So yeah, like I said, it needs a lot of memory. Indexing is slower if you have more dimensions, and merging is also slower. So ideally, you don't search during indexing. Especially for these full-text search use cases, you often don't have data that is changing that frequently. Maybe you re-index all of the data at night together, but you often don't have super frequent changes. Don't store the calculated vectors in the source, because that will just make your documents larger. Use fewer dimensions, and then the precision of each vector is by default float, so it needs 4 bytes. But instead, you can use a lower precision, so just byte for the precision, which is only 1/4 of the size. So it will use less memory and will be faster. And oftentimes that is close enough to give you almost the same results, but saves you 3/4 of the memory and hardware. Generally, how much memory this uses is, if we have a byte with 300 dimensions and we use the precision of bytes, one vector takes 300 bytes. You could have more than one vector in a document, so times the number of vectors you have in one document, times the number of documents you have in your index structure. So that will add up to quite a bit of memory over time. There's also, so that the 2 optimizations that you can do to reduce the memory is use byte instead of float, as I've said. And the other thing is, and I have completely forgotten that, or I have never learned it at university, I don't know. I'm not sure if anybody else remembers that, but there is the principal component analysis, PCA, of how to reduce the number of vectors. You also reduce some resolution, or like how well defined the data is. But you can basically compress these vectors into fewer vectors and get a similar representation of those. Though, yeah, does anybody remember that from university? Yes, you do? Can you still calculate that? Yeah, okay, because I might have never learned that, I don't know. But there is a way to potentially reduce the dimensions. I think part of the problem here is that you need to have either all the data or a very representable set of the data to do the transformation. So you cannot, if you start from 0 in indexing data, you cannot easily do that reduction in dimensions yet. So you need to have at least, let's say, I don't know, a representative set of documents, like 10,000 or so, and then maybe we want to add that as a feature in the stack later on. We're not sure yet, to do that PCA analysis in the Elastic Stack as well, but that's more like a thought experiment we had. Which leads me to the benchmarking thing, because there are a lot of bad benchmarks out there, and this is my favorite comic around benchmarks, where under similar conditions you compare 2 systems, and you can see that the squid is much more intelligent than the house cat, because you've killed the house cat, and this is what a lot of the benchmarks out there do. There is, however, one good benchmark from a guy I think called Eric Byrne. He has ANN benchmarks that include a lot of different tools. The one for Elasticsearch has just been merged. I think it's not in the graphics yet. Lucene already is, but Elasticsearch will be as well. And you can see that Elasticsearch is approximately in the middle of all the vector search engines that are out there. It's not on the very fast side, but it's also not on the slow side. It's mostly because, since Elasticsearch is Java, and neither GPUs nor native optimizations are very good in Java right now, we have the hope that as new Java features appear, we get closer to those native features, and that Lucene and Elasticsearch will actually be on the faster end of the spectrum for vector search engines. One side note of what is free and what is paid. If you bring your own embeddings or vectors and you search in vector search, the KNN search, that is all free. The thing how we pay our salaries is if you run that inference or the vectorization, for example, if you run the Hugging Face transformation in the Elastic Stack, that runs on a machine learning node, and that is a paid feature of our stack. So if you want to run that inference in the Elastic Stack, then that would be a paid feature. And then there is hybrid search. What is hybrid search? It's basically trying to combine a regular match query with a vector search query. Why do you want to do that? Because maybe you want to make sure that some specific terms are in there and you don't trust the vector embeddings. So the combination might give you the best result. Also, if you have a very short query that you're looking for, and you have a direct match, it can lead to very good results. Whereas the machine learning model often does best when it has more context. So if somebody enters a full sentence of what they're looking for, there's more context, and we could create a better vector around that. But if we search for something very short, the term-based search might actually be better. One pain point right now is that we do linear combination, so we basically add these two together. And the scale of the relevance that comes out of these two is not necessarily the same. So we try to fix it up with boosting one to be closer to the other one. But very soon, also in 8.8, at least the very first shot at that, there is something called reciprocal rank fusion, which basically normalizes the two scores against each other. And then you don't need to manually try to fix that up. And that will also come out in the next, or in the upcoming minor version to align those two. So you're basically combining term-based and vector similarity search, and then you get the best results out of the two together. One other thing to mention, because this is sometimes forgotten, you can combine those, and you can also combine searching across multiple vectors in a single query. So here I have an image vector, whatever the short image vector represents, and the title vector. So those can have different dimensions, and they can still all be combined in a single query. And you can see this one we boost with 0.1, this 0.5, and 0.9. You can still do boosting, but with RFF in the future, it will at least not be necessary unless you want to make one more relevant than the other. But all of this is possible, and you can combine these. Yeah. And then there is ChatGPT. I recently asked ChatGPT what is not great about ChatGPT, and then it errored out. But that was just, I think, a temporary overload. It can generally answer that question, but I'll rely on you. What is a problem about ChatGPT or large language models in general as they're implemented right now?
Hallucinations.
Mm-hmm.
Cannot trust the information.
Yes. Hallucination or fabulation is basically making things up. Since it doesn't really store knowledge, so for a large language model, the sentence, Neil Armstrong was the first man on the moon or the Mars. The only difference between the two is that the first one appears way more often than the other one. And that's why it will say moon rather than Mars. But it doesn't know. It doesn't really know the difference between the two things, or if they're related or not. It just knows that one is more common than the other. And sometimes things cross, and then random stuff or the wrong stuff comes out, which can happen. So that is a problem. Any other problems? So one thing that is sometimes surprising is
He only works on, like, takes data from before. It's not.
Yeah. Does anybody know what the cutoff time is, or what the answer to this question?
2020?
Yeah. So when I asked this question, it tells us that it was cut off in 21. So the last version is 7.15. So if I would ask it anything about vector search or KNN, it wouldn't know, because that was only added later in 8.0. So that is one of the downsides here of of a large language model. But the point might be that the language model itself makes sense, but you don't want to use it as a foundation of your knowledge. And that's what we have described in one of our blog posts here. We basically built the Elastic Docs GPT. So we take a query, we have a small Python application, and that Python application queries Elasticsearch and says, and in Elasticsearch we have stored all the Elastic documents, including the current version. And then we query, given the question that somebody asks, we query Elasticsearch and return the top one document matching that query. Then we go to OpenAI ChatGPT and we prompt it and say, like, answer this question with the one document that you have retrieved from here. So it will have current knowledge because it just looks something up. And it will not make something up because it's just based on the knowledge that we give it. So it cannot just make up a random API. Because I've seen that when ChatGPT once for me created a mix of Kibana and Elasticsearch APIs, which is totally not a thing. But it just mixed those APIs together. But here we're basically telling it only use the documentation here to answer my question, but use the language model of OpenAI to answer that. And how that looks like, we have that as a small demo running. I could, for example, say how to install Elastic Agent. That is not good. This is the demo effect. How to install, or our demo died. That's not good. Somebody deleted our demo.
Someone deleted the index.
Yeah, somebody deleted the index. This was working 2 days ago still. Okay, so unfortunately I cannot demo this to you then. That is a shame, because the nice thing is this looks up the documentation. It would even give you the link to the documentation, but it would still then give you a summary of, like, this is how to install that, and it actually gives you the right steps. Also, if you ask it a question that isn't possible to answer, so for example, if you ask, like, how to build a boat, then it would say, like, I couldn't find any documents for that, I cannot answer your question. So rather than making something up, it would just say, like, I don't know with the information that I have. Which is a shame that this doesn't work, because it would also show you how long the query in Elasticsearch takes, and then it would show you how long the query took in ChatGPT, and also what the query cost you. The one thing that then everybody will immediately mention is that, what if I don't want to give my data, or even that one document that I've retrieved here, what if I don't want to give that to OpenAI? Because in the current example, I'm handing out that one document. Well, you need a different language model, and there's a full family tree at this point of large language models. So it all started with Word 2 back in, I don't know, 2014 or something like that. And there's the BERT family over here, and then there's the GPT family over here. And you can see the different companies active here, and you can also see there are closed source models and open source ones, and the open source ones you can often run yourself on your own hardware as well. So if you have information that you want to, where you want to use a language model, but you don't want to give it to anybody else, you could just run the language model plus Elasticsearch locally or on your own hardware on-prem. Query the data from Elasticsearch, use your own large language model to answer the question, so you get the features, but you don't have to hand out your information to anybody, to the outside world. So you can do that, and you then just need to find the right large language model that you can have in here. So to wrap up, there's the traditional search, which is fast and cheap and dumb, or maybe limited. There's the vector search, where you need to find the right machine learning model to extract those vectors, and then find a model that works and the number of dimensions that can represent your documents well. Hybrid search tries to combine the strength of the two. There are some implementation limitations right now, but we are, like with the RFF, to normalize the scores, but we are working on fixing that. One thing, by the way, that is a bit of a limitation is, in a traditional search, I can easily highlight why something matched. With vector search, that doesn't exist anymore, or at least not so easily, because you have a vector representation and it's not a specific term that matched, so you get documents back, but it's much harder to say like why, which I don't know if that's scary or that's okay as long as the search result is good, but that's just a side effect of this search. One thing that it could also be interesting for vector search, since our stack is all about searching in different types of information, that you could, for example, model a security event or an observability event as a vector as well. And then if you're looking for security events, you say like, what was similar in terms of vectors to this event? Were there any other similar security events that had slightly different parameters, but have a similar shape, if you have a good model to extract kind of like important features of a security event? So we still do search, but it still bleeds over to security and observability, because you can represent a lot of things with these vectors. So that's what we're doing here. One final thing, one thing that is also coming out in 8.8 is something called ELSER, the Elastic Learned Sparse Encoder. What this does is it takes your text and it tries to automatically enrich it with synonyms that are weighted. What this looks like is if I have created an ingest pipeline to analyze my text here, where I run this ELSER model that we have developed on a text field. And what I'm doing now is I just simulate here. Again, this is pretty similar to what we have done with the analyze endpoint. We just simulate. I say, I take my original sentence, these are not the droids you're looking for. And I want ELSER to basically enrich this with synonyms that are correctly weighted for my text to make the search much more, I don't know, powerful or expressive. So what this does is I get, these are not the droids you are looking for. And then it says, I don't know, ship, dragon, quest, space, robot. And you can see these are the weights, how relevant they are. The higher, the more relevant they are. You can see looking, worse. So it has all of these as enrichment it could add. And then when you search for something, you would also run that through the same ingest pipeline, get a similar set of words, and then it would hopefully find more relevant text that is not just limited to those tokens. And we spent quite some effort on that model that hopefully covers a lot of use cases. It is, like most machine learning models, language specific, so right now this only works for English. If you give it a Spanish text, weird stuff will happen. Or I think I've done a talk about search in Spain once. Let me see if I can find my phrase. And you can tell me if this is correct. And by the way, if I run this against the English analyzer, what will happen? Nothing good, because the rules will not match. So here it will just chop off some stuff, but this will not give you good results. What you would need to do instead is you would need to say the analyzer is Spanish, and then it would apply the right words, and then that works. If I do this for the Spanish text with ELSER, I haven't tried this out. I hope nothing bad comes out. Because I did that 2 days ago at a German-speaking conference, and then it always said like that it's a Nazi speaking or something like that, because the German texts that it learned were often from that era. It's kind of like understandable, because it learned, I think, from Wikipedia and other sources. So there was a lot of recognition to that, but we'll fix that. So I hope nothing is bad in here. But it says Mexican. I don't know why it might say Chinese. Google, yeah. So for for other languages, it often doesn't make a lot of sense. I'm wondering. Yeah, okay, it's also a poem. I think all foreign languages are classified as a poem. So for example, when I did the same for French, it's also, I think for French it also says love. So no, you don't seem to have love in Spanish, so. But so it seems to have more learned about the context of a language than for the right language, and that is one of the big problems of models. So for example, there were machine learning models that learned, for example, when somebody worked on a construction site and they tried, I think, to identify dangerous scenes or whatever. And what the machine learning model under the hood learned, without you really understanding, is that everybody was wearing a yellow hard hat. And at some point, they switched to white hard hats. And then the model totally broke because it learned kind of like how the yellow hats were moving. And when you switch to white hats, because nobody really understood how the machine learning model worked, it just learned from the information you gave it. And that's kind of like the problem of these machine learning models, that you have a very hard time figuring out why something is the case and how it works. In many cases, if you try to train it with the right data, it gives you good results, but it's hard to figure out why. Yeah, we've seen those. And coming back to the start, we do search both traditional, vector, and hybrid, but we're sticking to for search because that's still the foundation of everything we do. And that's kind of like the entire point of this talk. I hope that made sense. Any quick questions before we eat? Otherwise, we can discuss over food as well. Yes?
I have one. How are you seeing the clients adopting that technology? I mean, are people looking at vector sets like adopting, just applying that in very small use cases, things like that? Or you start to see like just, well,
no,
let's put that in the core.
It's definitely getting more widely adopted. So I think search has quite a spectrum of users. So there's those who want to do stuff with minimal effort, and those are probably still not going full-blown vector search, maybe with ELSER, because ELSER is, by the way, not vector search. ELSER is just doing, we have implemented a search that is term-based and can take these weights into account, but it's not vector search. And maybe that is simple enough because you don't need to spend the money on vector search, and you don't need to train a model or bring a custom model, but you can just do that. And then there's the other side of the spectrum. It's like an e-commerce shop that makes millions a day on people searching stuff and finding the most relevant stuff. And they have been using vector search for quite a while. They might have calculated the vectors outside, but they then calculated things with those vectors for a while. So I think we had a big German e-commerce store, and they did a vector search talk a year ago already. And it's getting more widespread as it's kind of like leveling up the level of what people expect from full-text search. And it's not just like searching for terms and then somebody defining hundreds or thousands of synonyms, but that it's really trying to get the meaning out of a text and then find something similar in meaning and not just this term-based approach. So it is definitely getting more widespread. Though a lot of people will still be very okay with the traditional search for their scenario and also don't want to pay the price or effort for going further.
Can I make another one?
Sure.
How that relates with sharding? Because I would imagine it's completely different. So
I mean, the sharding, it still works across shards. It's still the scatter gather that we have, or query then fetch. So it will try to find the locally optimal vectors, I think. And then on the coordinating node, it will then figure out which are the overall closest vectors, and then it will retrieve those documents with the overall closest vectors. So sharding shouldn't be a limitation from what I know.
I mean, the concept of key of shard doesn't make any sense. I could imagine, but I don't know if it applies.
So the way the sharding is implemented, so for Lucene doesn't know about shards. So it just has it always assumes that the one shard is the full index and just gives you the local optimal results. And then the coordinating node figures out what is globally the optimal results and will only retrieve those. And that shouldn't really change from traditional search to vector search. I hope that makes sense. The only other limitation, though, is that you should have as few segments, because each segment has this HNSW, the small world, whatever, and you want to have as few small worlds as possible to search in those. Otherwise, your search gets very expensive. So you want to force merge to one segment per shard in most cases, which you only want to do if you don't write very actively to a shard. But that is the single most thing I think that will make your searches faster, besides using only byte rather than float precision. Those are the main things to keep your search relatively fast. Cool? Yeah?
I have a question. For example, if I have a video of a dog, I don't know, a Chihuahua dog, and I want to store it in vector in Elasticsearch, how I look later in vector?
So Elasticsearch is not good with binary data, so you would need to do that vectorization outside of Elasticsearch, and then you would only store the metadata, so the vectors and maybe some other metadata like the date or the author or whatever in Elasticsearch. And then when somebody searches for dog or Chihuahua or whatever, the machine learning model hopefully can match that to the kind of like what it extracted from the video, and you would still use the search for that in Elasticsearch, but the binary data itself would not be in Elasticsearch.
You only store the result of the recognition process.
Exactly, you extract the metadata and the vectorization, you extract that and store that, but the binary data would need to reside somewhere else. And hopefully your model catches that, but that depends on the quality of your model.
But that means that from the input text, there's somehow you can resemble a vector that can be matched again, a vector that came from binary data, right?
Yeah, right. So for binary data, you need to do that calculation of the vectors outside of the Elastic Stack, because you cannot send binary data. I mean, yeah, you can send it base 64 encoded, but that does don't do that.
But then how do you build up the vectors the match that you want to find? How do you construct this from?
So you will need a model that extracts, that maybe has like detection of things in a video. And then you will need to have another model to, if somebody searches for those things, to encode those as a vector. But you will need to have the right combination of models to find things, or one model that works for both. But normally you have a different model for binary data, or like one for audio and one for video to extract certain features than you have for text.
And you see if everything is text, usually it's the same model.
Yeah, then you normally use the same model, yeah. Or, I mean, the traditional way was that you would try to do some tagging on a video, like you ran a machine learning model and then you applied some tags to it, and then it would say, hopefully dog, and then you just do a full text search on dog of the metadata. But then you don't need vector search, or then you don't have vector search, even though you have a machine learning model involved in the process. Pizza time? Yeah. Is it working now? That's nice of them. And I did, just for the record, now it works. I did not delete this. Yeah, so how to install Elastic Agent, and this might take a while, so you can see we're running. And so this is the answer that ChatGPT is generating for you. So it gives you all the steps. And down here you can see how long did my query take. So that was not very long. And then you can see how much it cost in OpenAI cost and how long that took. And down here you can see that the number one result that you found in the documentation, and the number two result. And out of these, my hit was generated here. So this is how this plays together. Did they know that it was deleted, or did you just tell them that?
I just told them.
Okay.
Somebody else also reported it 2 hours ago. And
Okay.
Yet, so.
Thank you. Then somebody did a no-no. Yeah, but this is how this works in combination. Cool. Thanks a lot.
Thank you.
Pizza.